this lecture is a continuation of the lecture we did in SN2 reaction. Now, another example of SN2 reaction is the reaction of 1-bromobutane with sodium methoxide to give 1-methoxybutane. Now, like I said, that SN2 reaction leads to the formation of a varieties of functional groups. Like you can convert one functional group to another using SN2 reaction easily. So let us write out 1-bromobutane. Now, bromobutane is something like this. You have bromobutane is CH3, right? CH2, and then we have CH2, CH2Br plus sodium methoxide. Sodium methoxide is something like this. All right, that is bringing out the nucleophile in it, which is the oxygen. So this will react with this to form CH3, CH2, CH2, CH2O, CH3 plus sodium bromide. All right, which this is our 1-bromobutane. This is sodium methoxide, and then this is 1-methoxybutane, or you can just say methoxybutane. And of course, this is a byproduct, which is sodium bromide. Now, how does this reaction occur? That is the reaction mechanism. Now, let me see if we can put it in this position. Now, in this case, what I'm going to do is I'm going to actually talk about the stereochemistry of it. You know, the stereochemistry of SN2 reaction, I said in the first video that is going to give us inversion of configuration. So if the configuration were initially X, this is going to give us R. However, if the configuration is R, it's going to give us what? X. Using the Cann-Ingold-Prelog principle of naming compounds, or of naming isomers, if you can still remember. Yeah, we did something like that, talking about different kinds, stereoisomers, which are stereoisomers. So we have something like this. In the stereochemical form, we have the carbon, then we have Br, right? Then, of course, we have this hydrogen that is indicated with a broken line. If you can remember, we said this broken line means away from us. These are things that we learned in our year 1, and then this one means this is the wedge structure. Are we getting it? Holding them together, which is hydrogen. And then this is CH3, CH2, CH2. All right. Now, if you have something like this, and then you have the nucleophile coming to react. Now, in this case, we know that not every part here is part of the nucleophile, right? The only part that we are considering is from this part up. So we have it as O. The nucleophile usually attack from the back. That is backside attack. So I'm going to put it here. CH3. Then we have oxygen, which is CH3O, right? And then we have the lone pairs of electrons on oxygen, of course. And then we have the negative charge. If you can remember all this we did. Now what happened? This one here, which is this nucleophile, will come and it will form a bond with this. So as this one is coming here, the valency of carbon now will not be how many? If you count, this is 1, 2, 3, 4, 5. This can't happen. So this bromide, you know, this bromide is still having its lone pairs of electron here, will be given off, right? So the product of this reaction will be something like this. Then we'll pass through the transition state. Now we said the transition state is not the same thing as the reaction intermediate. Transition state is just like a stage in which we pass through before it converted to product. It's not like an intermediate because you can't isolate the transition state. you can't isolate. When we mean you can't isolate, it means you can't get the transition state as a product. It happens within a twinkle of seconds, and then it definitely changes to the product immediately. So what we are going to write now is the transition state of this reaction, which we encompass. We say the transition state is the state whereby this nucleophile is coming to attach. So we use broken line to indicate the nucleophile coming to attach. So we have the nucleophile here, which is CH3, and then we have O. Of course, this one is coming to attack with its 2 lone pairs of electron here, and then we have this group here, CH2, CH2, CH3, and then we have the broken wedge hydrogen group, and then we have the other wedge. No, this is supposed to be hydrogen, and then you have Br with 2 lone pairs of electron. Now this will give us the product of this reaction. So the product of this reaction will now become, before I go into the product, of course, you know this transition state, this bromine here is what? Partially negative. This is partially positive, and then this is partially negative. All right, now the total charge here, positive and negative cancel, so the total charge here will be what? Negative. So we have a negative charge here. Now, of course, I told you that this transition state, you often indicate it because it's a high energy state with a double something like this. All right, so the product of this reaction will be this, which is CH3. Here will be O, C with its lone pairs of electrons, and then you have CH2, CH2, CH3, and then here you see there is an inversion of configuration. Here we have the hydrogen, and then here you have the broken wedge hydrogen. These things, they are very, very significant. That is to tell you that the configuration is what? Inverted. So this is the inverted configuration of SN2. So SN2 usually give products that are inverted configuration of the initial product. Now, if you can still remember your Can't-Ingroup principle in your first semester, in your year 2 and year 1, you agree with me that we said in Can't-Ingroup principle, we have, this is the carbon in the center. Then we assign priority to them based on their atomic masses, right? And then if you look at the atomic mass of everything here, bromine, we have the highest atomic mass. So we name bromine number 1. Then oxygen, we have the, okay, oxygen is not coming in here first. So we are just going to consider the ones around carbon first. So this one will be number 1, right? And then this carbon here will be number 2. And then of course, this one here will be number 3. Now the number 4th hydrogen is usually the one on this wedge structure. So our distance is going from 1 to 2 to 3. Now if you look at this view from like this way, this is anti-clockwise. So when it is anti-clockwise, if you can remember, we said it's sinister, which is S configuration. Now coming here, you have this group here. Of course, automatically this group becomes number 1, right? And then this group becomes what? Number 2. Then here number 3. We assign priority based on the one that have the highest atomic number attached to this carbon. The oxygen is attached here, carbon is attached here, here hydrogen is attached, hydrogen is attached. Now between oxygen and carbon, which will have the highest atomic number? Oxygen. So that's why we name this as number 1, followed by carbon number 2, then this one number 3, and finally this is number 4. So we say it goes in this configuration, which is 1, 2, 3. Is that understood? So this configuration now is what? Arrow, which is the rectus configuration. Arrow configuration because it goes in the clockwise direction. So this is what I was trying to explain to you about the stereochemistry of SN2 reactions. All right, so that is that. Now the energy diagram for this reaction is still the same thing as the one that we did initially. All right. Now let's look at the practice questions. It says under normal condition, the reaction of 0.5 mole 1 bromobutane with 1 mole sodium methoxide forms 1 methoxy at a rate of 0.05 mole per liter per second. What would be the rate if 0.1 mole 1 bromobutane and 2.0 mole sodium ethoxide were used? Now, the most important thing that you must know when you are talking about this particular question is the kinetics of SN2 reaction. And that's what I'm going to teach you now. Now, talking about the kinetics of SN2 reaction, we are talking about the rates. Kinetics have to do with the rate of reaction over time. Are you getting the rate at which concentration changes over time? All right. Now, the kinetics of SN2 reaction is in such a way the rate equation will be R is equal to, you started again. K. So we have it as R is equal to K, which is the rate constant bracket the nucleophile, or let me start with the substrate first, because it's SN2. We have the substrate and there you have the nucleophile. All right. So we have it as the substrate and the nucleophile. That means it encompasses the concentration of the substrate and those of the nucleophile. Now, from what you know about reaction kinetics, you agree with me that this is first order in A. Why? Because this is raised to the power of 1. First order in B, because this is raised to the power of 1. I mean, first order in the substrate, first order in the nucleophile. Then overall, all you need to do is to add 1 plus 2. So 1 plus 2 is going to give us 2, which is second order overall. And that is why we call it substitution nucleophilic bimolecular, because it's a second order reaction. So the kinetics of SN2 reaction is second order. Now, if you are given any reaction at all, for instance, let's say you are given the rate equation as R is equals to K A square and then B. Now, what does it mean? It means that with respect to A, this reaction is second order. With respect to B, this reaction is first order. So together, 2 plus 1 is 3. So we say together, it is the third order reaction. Same thing is applicable here. So this one that has nothing on top, normally if they want to write it, you see it as this. This is first order with respect to the substrate, first order with respect to the nucleophile, and second order overall. So this is the rate equation for any SN2 reaction. Now, any substrate that is given to you, you indicate it there and then you solve. So in this case, you have under normal condition the reaction of 0.5 mole 1 bromobutane with 1.0 mole. So we have two values that are given to us. Are you getting it now? So the substrate, I'm going to use X to indicate. So we say X1, which is the first substrate, the number of moles is 0.5 mole. Now, with 1.1 mole of sodium ethoxide, so we have the nucleophile. The nucleophile, I'm going to use N1 to indicate. Nucleophile is equal to 0.05 mole per liter per second. Oh, no. With 1.0 mole sodium ethoxide. So sodium ethoxide, which is the nucleophile, is 1.0 mole. Forms 1 methoxybutane at a rate. So they gave us the rate R as 0.05 mole per liter per second. What would be the rate if now they give you new rate, which is what would be the rate? R2, you don't know R2. If 0.1 mole bromobutane, so bromobutane is the substrate, so you are giving S2 as 2.0 mole, no, 0.1 mole bromobutane. So we have this as 0.1 mole bromobutane and 2.0 mole sodium ethoxide. Sodium ethoxide is a nucleophile, right? So we have N2 as 2.0 mole were used. Now, in this case, what you have to do in this reaction is you first of all find the rate constant. Are you getting it now? Because in this reaction, the rate constant was not given to you. Now, let me tell you something. The rate constant for every reaction or for the same kind of reaction is always the same. no matter the concentration of the reactant. Is that understood? The rate constant, that's why it is called a constant. For every reaction, is always the same, no matter the concentration of the what? Reactants. So in this case, if we find the rate constant for the first one, we'll be able to find the rate for the second one. Now, to find the rate constant for the first one, recall that let's write the rate of the reaction. Rate is equals to K bracket. The nucleophile in this, the substrate in this case is 1-bromobutane. 1-bromobutane is something like the CH3, CH2, 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 Br, and then sodium ethoxide, which is sodium OCH3. All right. So our arrow to find the K, what are we going to put in the value of arrow first? What is arrow for the first one? 0.05 is equals to K bracket. Our X1 concentration of the first substrate is 0.5. All right, bracket times concentration of the second substrate is what? Is not second substrate of the first nucleophile is 1.0. all right, so this gives us 0.05 is equal to 0.5 K, because 0.5 times 1 will give us 0.5. So divide both sides by 0.5. When this cancel this, our K will be 0.05. all right, divide by 0.5, and 0.05 divided by 0.5 will give us what? Now this is going to give us 0.1. The unit will be what? Let's try and figure out the unit. You know, this is mole. This is what? Mole. Not mole. This is molar, right? M. This is molar. M. Now, what can we do to get the constant? Or let's just leave it without unit for now. When we talk about other, we'll analyze the units separately so that we'll not waste time on this particular one. So our rate constant is 0.1. all right. Now, have we gotten 0.1 as our rate constant? The next thing we need to do now is, what will be the rate? We will need to find the rate now. If 0.1 mole 1-bromobutane and 2.0 mole sodium ethoxide, sodium methoxide were used. So what we are going to do now is very easy. What is our constant? Our rate constant K is 0.1. Now, what is our rate? Our rate is K bracket bromobutane, and then you have sodium ethoxide. All right. So at the end of the day, our concentration of bromobutane given, which is S2, the second substrate, is 0.1. So we have 0.1. Our N2, which is the second nucleophile, is 2.0. So we have 2.0. So that at the end of the day, arrow will be equals to, in place of K, we'll put 0.1 times, in place of this S2, we'll put 0.1 again, times, in place of sodium ethoxide, we'll put 2.0. And then our arrow will be 0.1 times 0.1 times 2.0. That will give us 0.02. So this will give us 0.02, and the rate constant, this mole per liter per second, and this will be the rate of the reaction. All right. So that is how to provide solution to a question like this. Now let's look at another one. We have another question here. The question says, at 30 degrees Celsius, the second order rate constant for the reaction of methyl chloride and OH is this. Now, whenever you are given any question like this, the first thing you need to do is to write the rate of the reaction equation, right? Between what? Methyl chloride. Methyl chloride is CH3Cl and what? OH negative. Now this reaction is SN2 reaction, so the product will be CH3OH plus what? Cl negative. Now here this is our substrate and this is our nucleophile. So the rate of the reaction now will be equals to K Since it's SN2, it requires the substrate, all right, and the nucleophile. Let me use this to indicate the nucleophile. All right, so say the second order rate constant for the reaction of methyl. So you are given the second order rate constant as 1.0 times 10 raised to the power of minus 5. So we have our K 1.0 times 10 raised to the power of minus 5. Where's the unit? Mole per second square, something like that. Okay, now what is the rate of the reaction when the concentration of both reactants is 0.2 mole? Now the reactants are the substrate and the nucleophile. So the concentration of the substrate is equal to that of the nucleophile, and that is 0.20 mole as was given in the question. All right, 0.20 mole. Now substituting into this equation, R will be equals to what? It's very easy. We have our K 1.0 times 10 raised to the power of minus 5. Let's leave unit out. The substrate is concentration equals to that of the nucleophile, right? Which is 0.2, 0.2. So we have 0.2 times 0.2. Now the reactants are the substrate and the nucleophile, because they told you that the concentration of both reactants are 0.2, so you put 0.2 there. And our arrow would be equal to what? This will give us 0.2 times 0.2 times 10 to the power of minus 5 times 1. Alright? And that will give us this 1, 2, 3, 4, 5, 6, 7. That will give us 4.0 times 10 to the power of minus 7 as the rate, which is mole per liter per second. This is the rate of this reaction. Alright? So as easy as that. Let's me count again. We have 1, 2. Okay, it's 10 raised to the power of minus 7. It's very obvious because 2 times this is 4. This will give us 10 raised to the power minus 2 minus 2. Okay, so that is correct. Now the next part of the question says, if the concentration of methyl chloride is decreased to 0.05, what will be the effect on the rate of the reaction and on the rate constant of the reaction? Now what does this mean? This equation, what does it mean? It means that if you decrease the concentration of any of these reactants, it will affect the rate of this reaction. Alright? If you decrease the concentration of any of these reactants, it will affect the rate of what? The reactant. So if you decrease the concentration of substrate, it means the reaction will what? The rate of the reaction will also what? Decrease. Now if you decrease the concentration of the nucleophile, the rate of the reaction will also what? Decrease. But one thing that does not decrease is the nucleophile. I mean the reaction constant. Are we getting it? The rate constant, because the rate constant is independent of the concentration. It doesn't depend on them. Are you getting it now? So it's constant, it's there. So what we are going to do now is, you will ask, if the concentration of methyl chloride is decreased to 0.05 mole, what will be the effect on the rate of the reaction? Now you decrease it to 0.05 mole. What does that mean? It means that you decrease the initial concentration of methyl chloride by what? 4. True or false? It's true, because 0.020 divided by 4 will give us this 0.05 mole. Alright? If you divide it, just press your calculator, divided by 4, this will give us 0.050 mole. Are you getting it now? So if you decrease this by 4, it means the reaction will also be decreased by how many? By 4. The rate of the reaction rather will also be decreased by 4, because this is direct proportionality. The rate of the reaction is directly proportional to the concentration of the substrate and that of the nucleophile. So anything you do to the substrate here, you definitely do it to the rate of reaction. So if you decrease this by 4, it means that the rate of reaction will be decreased by 4. Alright, so let's practice this and see if it's actually true by doing the analysis here. So what will this give to us now? The rate of methyl chloride is 0.05, which is a substrate. So it means our K still remains as 1.05 as 1.0 times 10 to the power of minus 5. Right? And that of the substrate now is now 0.05 mole. Now recall that of the nucleophile still remains 0.20 molar. Alright? This capital letter M. So our rate now, of course, you know, is substrate. Let me use this to abbreviate, and nucleophile. So our rate of reaction now will be equals to 1.0 times 10 raised to the power of minus 5. The substrate now is 0.05 times the nucleophile is 2.0. Still remains the same. So R will be equal to, when you multiply this, what is it going to give to us? 1 times 0.05 times 2.0, not 2.0, times 0.2. Alright? Times 0.2, not 2.0. This is 0.01. So we have 0.01 times 10 raised to the power of minus 5. R will be equal to this 1.0 times 10 raised to the power of minus 2 times 10 raised to the power of minus 5. If you don't understand what I just did here, please don't bother. Just press your calculator from here and get your answer. Alright? So that will give us a sum. If you multiply this and this, that will give us 1.0 times 10 raised to the power of minus 7. Now, can you see the differences now? When you decrease this by 4, the substrate by 4, you discover that the rate of the reaction was also decreased by what? Was divided by 4. Look at it. We divided this. If you divide this by 4, 4 divided by this will give 1, which is 1.0 times 10 raised to the power of minus 7, which is what we got here. So you see that anything that you do to any of these reactants here will definitely affect the rate of the reaction. So it means if I also decrease this by 4 now, it means the total rate now will be decreased by 4 times 4, which is what? 16. Is understood? If I decrease this by 2 and then this one still remains, it means we have to divide this by 2, which will be 2.0. Then if I decrease this by 2 and decrease this by 2 again, it means the something will still fall back to 1.0 because you are decreasing it by what? 4. Alright? So that is how to go about this. Now, you say, what will be the effect on the rate of the reaction? We've discussed on the rate of the reaction. It will lead to a decrease in the rate of the reaction by 4, which will now have a rate value of 1.0 times 10 raised to the power of minus 7. You must actually indicate this, you must calculate this, and then show to the lecturer what you are doing. Alright? The next one is, what will be the effect on the rate constant of the reaction? Now, I told you that the rate constant, it does not actually, is not affected by decreasing the concentration of any of the reactant because it is a constant. It does not change. A constant does not change. So, there is no effect on the rate constant. There is no effect whatsoever on the rate constant. Alright, there's no effect whatsoever on the rate constant. So that's how to go about solving questions like this. You see, it's pretty easy, right? It's pretty easy. So that's basically all you have to know about the rate of this reaction, and also how to calculate rate of reaction for SN2 reactions. Now, you can go through this again over and over. For this particular one, what we did first was to calculate the constants, since the constants were not given to us, by using the first parameter that was given. Now, have we got to the first parameter now, or have we got to the rate constant? We can now use the constant to find the rate of the second parameter. Is that understood? Because we know that the constant does not change. Alright? Does not change. So thank you very much for your time, and God bless. So what you are going to do here is to write the rates of this reaction, or the energy diagram. You know what to do, right? We say the energy diagram of the reactant is always higher than that of the product. You have bromobutane. You write bromobutane here plus sodium methoxide. Then you have the transition state. You can practice this. You have the transition state. Of course, I told you use this symbol to indicate that it's a very high energy state. And then you have the product here. Of course, here what you have here is the energy, and then here what you have is the reaction coordinate for this particular one. So that is basically where we are going to end for this lecture. Thank you very much for your time, and God bless. Make sure that you subscribe to this channel, turn on the notification button so that you'll be notified whenever we post a new video. Bye.